All right, so last time we went ahead and learned about what the derivative of the logarithmic function is ln of x. We know that the derivative of ln of x is, well, 1 over x. So this is what we sort of left off on last time. Can someone go ahead and tell me real quick, why did I bother putting this second derivative, the derivative of the absolute value of x? Why did I bother putting that derivative as well? Well, what would there be confusion about necessarily? Mm-hmm. Yeah, and to follow up on that, why is it that the top one, we only allow x to be positive? What happens if I try plugging in a negative number into a logarithm? What would happen if you try putting that in your calculator? It would give you an error, right? So by putting these little conditions, we're just being a little bit extra careful because we know that a lot of times we like taking the derivative and then plugging in a number, for example. So this is just us covering all of our steps, making sure that we're really looking at everything. So this was our theorem. So let's go ahead and look at this example. Example 3. Let's get the derivative of y prime if I know that if the function is y is equal to 3 natural log of 2x minus 8. So let me go ahead and pull up this pen. I want the derivative of y prime. So looking at this function, what derivative rules do you think would be handy? Well, first off, do I really need a product or a quotient rule? No. I heard someone right before I started said chain rule. That's definitely going to be useful here. And then obviously we have a logarithm. So we're mainly going to be using our chain rule and then derivative of the log function. So on the side over here, we're going to do our classic, let's list the layers and then the derivative. The layer and then the derivative. What is my first layer? Yeah, 3 ln of something. 3 ln of something. And then my second layer, yeah, we got 2x minus 8. All right, so I know I'm done with all my layers because I've accounted for everything. 3 natural log of 2x minus 8. Now I need to go ahead and deal with my derivatives. So for the first layer derivative, I'm going to go ahead and write the 3 down because we know coefficients, but they're just going along for the differentiation process. What's the derivative of natural log of something again? Yeah, 1 over x, bless you. Or in general, 1 over whatever that something was. Because we don't have natural log of x, we have natural log of something else. So that's my first layer. And I'm remembering whatever was in this empty spot, that's also going in this empty spot. What about the derivative of layer number 2? 2. We know that the derivative of 2x minus 8, we just get 2 from a very nice, straightforward power rule. All right, so now I have my layers. I've got the derivative of each layer. Now I just need to put them all together. Derivative of layer number 1 is 3 times 1 over, what am I putting down here in the denominator? Yeah, 2x minus 8. All right, and then I also have times the derivative of the second layer, which is 2. And then we're done. If you want it, you could simplify this just because it's really quick and easy to simplify. Really, all I can do here is saying 3 times 2 times 1. We get 6 over 2x minus 8. As another note, is there a way that I can further simplify this down if I wanted to? Yeah, so if I'm looking at this, I'm noticing that everything is divisible by 2. So I could factor a 2 out from the top and 2 from the bottom. This is just for the sake of completeness. This could be the same thing as 3 over x minus 4, for example. So this is the simplified answer. The main reason I simplified this one is that we didn't really have any complicated multiplication here. It's really just 3 times 2 times 1, and then factoring out an even number, the even number 2. Yes. And usually I'm letting y'all do this first line for the sake of everyone's sanity, so that we don't have to deal with a very complicated simplification. Whenever it's something like this, I might do it occasionally where I simplify it. Like, let's say on one part of a derivative, we got 4 minus 4. If it's something like quick like that, you can, but I'm not going to be too concerned about it. The natural log, 3 times the natural log of 2x minus 8, sorry. And I'll give y'all some time to copy anything down as needed for this problem. So again, this uses our chain rule and a derivative of the natural log function. We are going to just very briefly later talk about general log functions. Here we're using the natural log because of its relationship to e to the x, but we could extend it further, that, as you'll see in just a moment. Well, maybe not today, but maybe on tomorrow, depending on how far we get. Any questions about how we went through example 3? What? On a test, no, but in class, sure. I see that you're picking up on some clues for the future. All right, so we finished example 3. Let's go ahead and look at our next example. See if I can get this to work properly. Fair enough. Oops. Example 4. Give me the derivative if I have y is equal to 5x to the 4th times the natural log of x. So once again, I'll start off as per usual. What rules do you think are going to be handy here? Power rule, for sure. I heard someone say product. And then, quite obviously, our logarithm rule, because very directly I see a natural log. So I'm going to need those 3 rules for this problem. So I'm just going to go ahead and start off by just writing dy dx right off the bat. Oops, that's not a very pretty d. dy dx. All right, so here I have a product rule. What should I identify as my first, and then what's for my second? Yeah, 5x to the 4th, and then the natural log of x. One quick note, I want to, a small side note. Remember whenever we talk about the logarithm, it's very similar to the trig functions. We're not just going to write ln, it's ln of something. In other words, you're never going to say that this is just one expression. It's always ln of something. All right, so I have my first and my second. I'm going to denote it with 1 line and then 2 lines. Product rule. Product rule states that the derivative of a product is first d second plus the second d first. So we're just going to follow through with that. We have the first, 5x to the 4th power, times the derivative of the second. What's the derivative of ln of x again? Yes, 1 over x. First the second plus the second, ln of x. Remember, I'm using a sort of cursive L just so that we don't get it mixed up with an I or a 1 or anything like that. And then we need d first. What's the derivative of my first? 20x to the power of 3. So I've done the calculus portion.
So why didn't we use 5x to the power of 1?
For this part? Well, that's because my second is just ln of x. It's not ln of 5x to the fourth. You're thinking more if I had ln of 5x to the fourth. So really, this is its own separate entity, ln of x. You would be correct if we had ln of 5x to the fourth. We'd put that 5x to the fourth on the bottom. And that's one of the things that makes this tricky. Are we using chain rule or am I using product rule and stuff like that? But this is my unsimplified answer. In other words, the calculus portion of this problem. If I did want to simplify this, there's not much I could really do. I could clean this up, 5x to the fourth divided by x, that would become 5x cubed. But then for this other, there's not much I can do there. All right, so we're done with example 4 in its unsimplified form. Great, so we've done an example with log functions where we use the product rule. Any questions about this before I move on to example number 5? All right, so moving forth. Great, let's do dy dx, the derivative, if I know that I have y is equal to the natural log of 2x. So I'll state the obvious in saying that we need the derivative of a log function. And furthermore, I think we can also quickly agree that here I'm going to be using a chain rule because I have a function inside of a function inside of another function. So since we're using chain rule, let's go ahead and start off by just writing out my layers and then my derivative for each layer. So each layer. And then over here, I'll put the derivative. So if I look at this function, my first layer, the outermost layer, we have a natural log. So I'm going to write ln for my outer layer. I'm just going to put a star here to say that there's stuff in there. What's my second layer of this function? Yeah, we have a natural log of something else. I'm going to put 2 stars here. And then my final layer, yeah, we have 2x. Notice here that I didn't put a star. I didn't have another layer because I've accounted for everything. The natural log of 2x. And that accounts for my entire expression right there. All right, so now we're just going to go ahead and take the derivative of each layer. We already know what the derivative of ln of something is. It's 1 divided by that expression. So for the first derivative layer, I have 1 over whatever was in that same blank. Usually this would be an x, but I'm just putting a star there since it's something besides an x. Same thing for the second layer. We'll put 1 over whatever was within the second layer. What's the derivative of 2x? 2. Through a nice power rule. All right, so I have all of my layers. Let's go ahead and take the derivative dy dx. We have layer number 1. The derivative of layer number 1, we have 1 over, and what's going down there in the denominator? Yeah, so what's going to go down there on the bottom for the layer of the first derivative? Yeah, 1 over the natural log of 2x. Because again, this outer layer had all of this in there, so I'm still putting it in. This is my second layer, so I have 1 over, what's going to go in the second part? Yeah, 2x times the last layer, 2. And then I have my unsimplified answer. Again, I'm using here whatever was missing from this outer layer. That's still going into here. All right, so we have example 5, which is nice. We've done some more practice on chain rule, but this time with a logarithmic function. Any questions, comments, concerns about this example 5? So pretty much very similar to what we've been doing, but now we have that natural log as an extra derivative to work with. All right, so let's move on from here. I can't remember if I have an example 6 or is it the next part of my lecture. So let's see. So moving on from example 5, let's go ahead and talk about the properties of a logarithm. Oops, go back. So these are just some general properties of a logarithm that I want to mention. I'm going to see why I might want to use them. So if I have any two real numbers, I'm just going to call them A and B. Remember that we talked about this notation before? Remember that this is just fancy shorthand for saying for all numbers A and B that are real. Or you say real numbers A and B. No matter what they are, then these properties of the logarithm must hold. This first one, I call it the product sum property. If I take the natural log of a product, then that is equivalent or equal to natural log of the first plus the natural log of the second. So a product inside becomes addition on the outside. And then we have a similar thing with the quotient. If I take the natural log or log in general of a quotient, this is equal to log of A minus log of B. In other words, I'm able to split up a logarithm if I wanted to, if there's multiplication or if there's division. So looking at this, why am I even introducing these two properties? There's two more I'm going to introduce, but why am I introducing these in particular to start us off with? So I know that we can always have a product rule. It's possible to have a product rule inside a logarithm. And that's a little bit of a messy chain rule with product rule embedded inside. The reason why I might be interested into this is that I can take a product inside and split it up, therefore avoiding a product rule when I do the derivative. Same thing here. Yes, it would still work if I do the quotient rule. It might be a little bit more involved, but it would be much easier to just do these individual rules rather than doing log of a quotient and then doing a chain rule with product rule and quotient rule involved on the inside. And you'll see what I mean whenever we get to the next example. So I'm introducing these properties largely because they're going to help us deal with a lot of these derivatives a lot quicker. In other words, I'm trying to avoid a chain rule with a product rule on the inside or a quotient rule on the inside. Oh, this is for all. It's like an upside down A. Yeah, it looks like an upside down A. It just means for all. There's usually not a dot there, but whenever I transfer the files onto the screen, it likes putting a dot there for some reason. I'll give you all any time to copy this. All right. So let's talk about the other two properties of the logarithm. Again, these are two other properties that can be really helpful. I call this next one the power coefficient property. If I have log of something to a power, I can actually push that power to the front of the logarithm. That is, log of A to the B power is equal to B times the natural log of A.
To be honest, I would think that you wouldn't really need to do this for power rule, because that seems easy enough.
For a basic power rule, we don't really need it, but you can imagine if I had something like natural log of natural log of something to a huge power, for example. In other words, I'm using these rules to sort of chip off some of my layers, because we know whenever I do derivatives, coefficients, they just go along. So again, all these rules, they're kind of letting us get around so many layers. Of course, there are some limitations that we'll see in a moment. And then the fourth property, I call this the change of base property. So I only gave y'all the derivative of natural log, but we know that there's a bunch of different other logarithms. There's log base 10, log base 4, stuff like that. How do I deal with those? Well, as it turns out, one of the nice properties of any logarithm, I can always write log base b of something, a, to be natural log of a over the natural log of b. Again, right now we're being a little bit abstract, just having a and b. You're going to see how I'm going to apply these in just a moment and why might they be useful for us.
The derivative of that's one over a over one over b.
Depending on which one has an x, we might not always have an x in both of them. Because one of them, just like natural log of 7, that's a coefficient, because there's no x's in there. You'll see what I mean in a moment. All right, so we have all these properties of logarithms. Let's go ahead and actually do an example. Something like this. So the first thing I'm noticing here is that if I did this straight away directly, then I would need derivative of a log function. I would need power rule. I would need chain rule, and I would need quotient rule. So a lot of rules here and there. And the thing is that we know that quotient rule, whenever it's on the inside of a chain rule, it kind of gets messy, like what we saw in one of our old examples. So using a property of a logarithm, before I even take the derivative, I can actually rewrite this. I can rewrite this as, we know natural log of a quotient is the same thing as subtraction on the outside. So I can write it like this. The natural log of 3x plus 1 minus the natural log of 3x minus 1. So I haven't done any derivative work yet. I just rewrote the original problem using a property of the log. So the reason I wanted to do this is that, yeah, I still need chain rule, but now I have no need for my quotient rule at all. In other words, I can go ahead and try to take the derivative immediately. dy dx. So without me listing out the layers for each one, because we have two separate things, for the first half of this part right here, what is the derivative of that expression, you would think? First off, what's the derivative of natural log? Yeah, 1 over x, but we don't have natural log of x. It's 1 over whatever's on the inside. So layer number 1, we get 1 over 3x plus 1. What am I going to multiply by next for this part? Let's see, we have 1 over 3x plus 1. Yeah, so this is the derivative of the first layer, because from natural log. My second layer is 3x plus 1. Derivative of that, we get 3. So just to make it clear, layer number 1 is ln of something. Layer number 2 is 3x plus 1. So this is where I'm getting each derivative. Derivative of ln, it's 1 over that expression. Derivative of 3x plus 1, we get 3. So I'm done with the derivative of that first half. Minus, now I need to do the second part. Fortunately, this is pretty much going to be almost the exact same answer. The derivative of the natural log of 3x minus 1, that's going to be 1 over 3x minus 1 times 3. First layer, second layer. And then I'm done. I'm going to take a moment and talk about what happens if I didn't separate these in the beginning. If I did not separate these, this would still be my first layer, but my second layer would be a quotient rule. So then layer number 1, yes, natural log of whatever. Layer number 2 would be this entire quotient. And then we would do the quotient rule as the derivative. So for this one, it doesn't seem like it helped us a whole lot. But you can imagine if I had something that was really big and complicated, it'd be nice to break it down and not do like 7 quotient rules in a row. Yeah, we can also simplify it. 1 times 3, we can do that real quick, right? We can do 3 over 3x plus 1 minus 3 over 3x minus 1. In other words, if you want to simplify it, it would be this. Minus 3 over 3x minus 1. That's a simplified form. Well, sufficiently simplified. Whenever I'm doing problems, my personal thing is more if I was trying to simplify, I try to do anything that's like quick multiplication or addition, going and putting those together. But again, we're not too concerned about that. We're mainly concerned about getting that derivative and doing the calculus portion. All right, so we have example 6. We avoided a quotient rule. Any questions about this example 6? All right, so let me go ahead to the next slide. This one, y is equal to log base 3 of x. So based off our derivative rules, there's not much that we can do here right now if I was strictly using the derivatives that we've learned so far. Because I don't know how to take the derivative of log. I know how to take the derivative of the natural log, but we haven't done log base 3, for example. However, we do have properties of the logarithm, in particular that fourth property that I had before, the change of base. Before I even take the derivative, one thing I could do here is change this log base 3 of x into the natural log of x over the natural log of 3. Again, this is my change of base formula. Basically, natural log of what was here and then natural log of the other value. And I'm going to take it even one step further from here. Natural log of 3, that's just a number. There's no x's in there. So to emphasize this, I'm going to go ahead and write this as 1 over the natural log of 3 times the natural log of x. Is this necessary? Not really. It'll help us see something. This is a coefficient right here. 1 over the natural log of 3. It's some ugly number. It's like a decimal value. This is the only part that actually has an x in it. So if I want to go ahead and take the derivative, dy dx. We already said whenever I have a coefficient, it's just going to go along for the process. So I'm going to go ahead and just write 1 over natural log of 3 already. It's a coefficient. And now I'm asking what's the derivative of the natural log of x? What's the derivative of what I have here? Yeah, 1 over x. And then we're done. To write it what? So in this part, Based off what we have, for going from here to here, yes, because we don't know how to do derivative of log. We don't know how to do the derivative of the natural log. Going from here to here, it wasn't really necessary for me to write 1 over natural log of 3. You could have just said, what's the derivative of that? 1 over x, and then this just goes along on the bottom. Like, for example, if you want to go from here directly, you could have said, well, natural log of 3, that's a coefficient. What's the derivative of natural log of x? We have 1 over x, which would have been the same thing here. So, right, in other words, here it is necessary for us to use a natural log. There is a little bit of a pattern that some of y'all will see. If this was log base 4 of x, what do you think my answer here would have been? If this was log base 4 of x, instead of a 3 here, this would be a 4, right? So if this was like a 4, then this would be a 4. So the reason I mentioned this is that actually there is a derivative rule that sometimes people use, because it always ends up like this. Let me clear this, erase this a little bit. Okay, take that. Oops. Let's see. Guess it's not. I'll try to fit it in up here. Some books do have that the derivative of log base a of x, based off what y'all told me here, a lot of books, they like saying that it's actually 1 over the natural log of a times 1 over x, because of that rule about the change of base formula. So y'all told me if this was a 4, then this would be a 4. So whatever that number here, it actually always turns out that way. So some people, some books do include this as another derivative rule. The reason I'm not is that this is actually just an offshoot of the natural log. So whichever way you want to do it, if you want to know that formula or if you want to do it this way, they're both valid.
How in the world do we get it split? Because natural log of x was on top of natural log of 3. How do we get that?
Oh yeah, so first off, you recognize that this natural log of 3 is on the bottom, right? So it would be the same idea as if I had something like this. So if I had x over 2, that's the same thing as 1/2 times x. 1/2 times x. So in other words, we're used to sort of combining things into one fraction, but we're always allowed to separate things as needed as well. So that's what I did here, mainly because this expression, or what I have here, we don't really need to do any derivative work on that. That's a coefficient. It's a number. All right, so whatever way you want to write it, the derivative of this function was 1 over the natural log of 3 times x on the bottom. Any questions about this example 7? So what I want to do is I'm just going to show you example 8. We don't actually have enough time to go through it, but I just want you to, I want to show it to y'all, and then I want y'all to, I might show you the first thing I would do, but then we'll probably finish it on tomorrow. So let's see what's on example 8. 17 to the x power. We have no derivative rule for this. We have e to the x, but we have never seen a derivative of any other number to a power of x. And let's say I want my final answer in terms of x only. So looking at this, does anyone have any idea or something that we might be able to do here? Maybe something that involves our logarithms. I see I stumped you with that.
Do we turn it into a regular log, or is it like log 17 times x?
Sort of. So I'm just going to show you the first couple of steps, and then I'll leave it at that. So what are one of the big rules in algebra about playing around with an equation? Well, one of the big rules in algebra is if I have an equation, I'm allowed to do whatever I want as long as I do it to the left and to the right. Like back in algebra, you said, okay, I can subtract 1 from the left as long as I do -1 on the right also. So using that idea, it's perfectly legal for me, for example, if I wanted to write something like this. Is it weird to write this? Yes. But I did natural log of the left and the right. So these are still equal to each other. And why does that even help us, possibly? Particularly, why does it help us on the right? Think about those log properties. So in particular from those rules, the one I'm thinking about is that power coefficient law, where it says if I have a power on the inside, I can pop it out to the front. In other words, this is the same thing as this here. Because I know how to take the derivative of that. That's a number times x. I know how to do the derivative of the left as well, but then this is where I would start. And this is actually a good part for us to stop, because what I did here is I'm going to try to take the derivative of this next equation, doing implicit differentiation. And what we're going to see is a technique called logarithmic differentiation, where we use a log to clean it up and then do the derivative afterwards. So this is where we're going to stop today. If you want, you can try finishing this and see if you can get it tomorrow. We still have examples 8 through 11, I believe, which we'll finish tomorrow, if we can. All right, besides that, that's all for today. I'll see you on Tuesday. Let me go ahead and end the stream here.